Now coming to the derivation of this center of mass of a solid hemisphere as x bar comma y bar, we'll spend some time. Okay, let's say it like this. We'll divide this derivation into two. One will be to visualize the three-dimensional aspect of this solid hemisphere. Two will be to derive it mathematically. Okay, and of course arrive at this formula. Okay, so let us see how to understand the visualization. So we'll first discuss this in 3D. Well, of course, not possible in pure 3D. We will discuss in pseudo 3D, and then we'll try to analyze it in 2D. So usually we call this method as the stacking disk method. Why is it called so? Because we stack many disks one over the other to find the center of mass of hemisphere. Okay, so this is what we have here. Okay, so imagine a solid hemisphere. Oh, excuse me for a second. Yeah. Imagine a solid hemisphere placed on the xz plane of the three. This is where the plane and the height along the axis becomes really important of the 3D space. The flat circular face lies in the xz plane, and the curved surface extends upwards along the y-axis, and that is why we got the answer as y bar is equal to 3r by 8. Okay, right. So the full sphere existed its center would be at origin 0, 0, 0. But since we only have half, therefore the hemisphere, it extends only in the positive y direction. To understand the shape, imagine slicing the hemisphere into thin horizontal circular discs stacked along the y-axis. Each disc represents a small cross-section of the hemisphere at that specific height. The size of each disc will vary according to the height. It will be larger near the base, and as we go up along the y-axis, it will be smaller. The topmost disc therefore will be the smallest, and the bottommost disc will be the largest. Now, one more time. The flat circular face lies in the xz plane, where y is equal to 0, and the highest point of the hemisphere here would be y is equal to r. Okay, so the smallest point is y is equal to r, and the bottommost point is y is equal to 0. Yes, I do understand that without the diagram, you're not able to follow what's written here. We'll come to it. We'll slowly come to it. So the first step here would be to analyze the mass distribution. We slice the hemisphere into infinitely small horizontal disk along the y-axis. Each disk is a small circular slab, or a cylinder, with a specific which is kept at a specific height y from the origin. The thickness of each disk is dy. Now let's see the visualization part. So this is what was mentioned earlier. This is a small disk, okay, of thickness dy, where dy actually tends to 0, which means the disk is very small. Okay, and the radius of this disk is, say, x, or say better to say xi. Now this can be assumed to be a cylinder or a slab. Okay, now this disk is placed along the three-dimensional axis 0, 0, 0, such that this represents the positive x-axis, this the positive y, and over here this represents the positive z. And this disk is kept at a height y1 from the origin, okay, and has a radius x1 which is having a thickness of this. So this thickness here is dy, and this measure here is r. Okay. Okay, I don't want to repeat things here. Maybe we'll go to the next test. Things will become really clear to you then. So let me just erase it out, these values. Okay. Now imagine we have another disk 2. Let's draw things one more time. Things will become really clear to you. This is x2, the radius. The thickness remains the same, dy. This is at a height y2, okay, and all of this such that this value is r. Okay. So now we will combine these two figures. And what do we get? We get a stack of two disks. Disk 1 with radius x1, height y1, and thickness dy. Similarly, disk 2. So this is x1. The larger distance here becomes x2. Therefore, x2 is greater than x1, right? And dy is same. Now, how will be y1 and y2? This height will be y1, and this height here will be y2. Okay. Now, what are we trying to achieve? Let's see. If we have another disk, which is disk 3 of radius x3, right? So this here would be what? x3. Now you will tell this, which is y3. This value remains exactly r, right? Okay. And the radius of each disk depends upon its height. The largest will be at the base, and as we go up, the radius of the disk will become smaller. The closer the disk is to the top of the hemisphere, the smaller will be its radius, which is what we see here. x2 is greater than x1, right? Okay, things will become more clear on this. So what do we have here? We have 3 disks, and now the radius will be x3 is greater than x2 greater than x1, right? So what next? Disk 4, same thickness dy at a height y4, and then if you stack all 4 of them, what we get is x4 greater than x3 greater than x2 greater than x1, right? We have a stack of 4 disks, concentric disks. Similarly, if we add one more, we get x5, x6, x7, x8. Now, if we have observed really close these diagrams, in every diagram, what we see is that the blue arrow remains at the same position, which means the blue arrow, all these disks are being generated at a radius r along this axis. So we have x6, x7, x8, and as the number of disks increases, it increases even further, and when say it comes like this, at this point, imagine that this stacking of disk, it is appearing to assume a shape of an outer boundary like this, right? See, there might be some spaces here which you feel is void. That actually comes due to the limitation of drawing in using a digital board. So when you draw it in your paper, these void spaces would be really less, and that becomes even lesser when the number of these disks when the number of the disks tends to infinity. Then what we see is that the overall shape assumes the overall stacking of disk assumes the shape of a hemisphere, right? And along the surface of the stacking, the radius, that distance remains the same, which actually is the radius of the hemisphere, right? So now if you consider any disk at a height y from the origin with thickness dy and x as a radius, so if you take one such disk like this, if you see, this is where the diagram of a disk becomes really important, and it is this triangle which lies the mathematical basis for the derivation of the center of mass. So what is this height? This is yi, this is xi. What remains constant is r, and what we get is a right angle triangle. Okay, so if this visualization is clear to you, and if we consider only the triangle, then what are these values? These values here, as we said, are x, y, corresponding y, constant r, and definitely the thickness dy, right? And from this triangle, we can say that by hypotenuse, by Pythagoras theorem, we can say that x square plus y square should be equal to r square, right? Now, see, well, actually, this is a jugaad way of coming into this expression. The more mathematical way would be coming to the equation like this. The equation of the sphere will be x square plus z square plus y square is equal to r square, which is actually extrapolation of equation of a circle. X square plus y square is equal to r square in 2D to 3D, which with another coordinate z, right? Now, we know that x square plus, okay, see, if you understand that this complete figure is placed along the xz axis, which means we have a circle which is along the xz axis. And what is the equation of a circle along the xz axis? The equation of a circle along the xz axis becomes x square plus z square is equal to r square. Why? Because x minus 0 square plus y minus 0 square becomes r square. Yeah, see, a lot of things on the board right now. I do understand the difficulty in this. So write this along with me. X minus 0 square plus z minus 0 square is equal to r square is the equation of a circle, equation of a disk which is lying on the lying on the xz plane. Now, if x square plus z square is equal to r square, then can we substitute this fraction over here, x square plus z square, as r square? Therefore, this equation becomes r square plus y square is equal to capital R square, or r. Okay, now you may have a doubt. What is r? R is the radius of the disk. What is capital R? It is the radius of the what? Of the hemisphere. And therefore, we have r is equal to capital R square minus y square, and therefore r is equal to root of r square minus y square. Now, why is this equation being discussed here? What is the significance of this? Now, okay. The formula tells us that there is a quadratic variation between r square and r, which means at y is equal to 0, right? When we have y is equal to 0, the radius is maximum, which is equal to r. Oh, well, I'm sorry for these values here. It's not triple r, it is r. And when y is equal to r, at this point, which is the top of the hemisphere, the radius is 0. Maybe I'll just write it for you. Things will become more clear. So when y is equal to 0, what is the value of r? It is equal to root of r square minus y square, and therefore r is equal to y square is 0, which is root of r square, and therefore r is equal to r, right? And this is the maximum value. So this represents the topmost disk here. But when y is equal to r, What is small r? The radius of the disk is becomes root of r square minus r square, which is equal to 0. My bad. This should be the largest point here, right? Not the smallest one, the largest one. Now, r is equal to 0, which means radius of the disk is equal to 0. When the radius of the disk is equal to 0, it means the topmost point over here. Why? Because there we have only a very small figure. See, this is this is the point where actually the concept, the mathematical part of the JEE mains, especially when you're preparing for JEE mains, the visualization and the concepts that you have learned in three-dimensional surfaces in class 11 becomes really important, because these are the regions where they get integrated into one. Also, this is one such section where you can expect a assertion and reason based on the location of center of mass, not on the coordinate of it, rather on the dependence of height. I hope that makes sense. Okay, so that is about the visualization of the concept here.